In mathematics, a complex structure on a real vector space V is an automorphism of V that squares to the minus identity, minus I. Such a structure on V allows one to define multiplication by complex scalars in a canonical fashion, so as to regard V as a complex vector space. Every complex vector space can be equipped with a compatible complex structure, however, there is in general no canonical such structure. Complex structures have applications in representation theory as well as in complex geometry, where they play an essential role in the definition of almost complex manifolds. By contrast to complex manifolds, the term complex structure often refers to this structure on manifolds. When it refers instead to a structure on vector spaces, it may be called a linear complex structure. Definition and properties. A complex structure on a real vector space V is a real linear transformation such that here J2 means J composed with itself and IDV is the identity map on V. That is, the effect of applying J twice is the same as multiplication by -1. This is reminiscent of multiplication by the imaginary unit. A complex structure allows one to endow V with the structure of a complex vector space. Complex scalar multiplication can be defined by for all real numbers x, y and all vectors v and v. One can check that this does, in fact, give V the structure of a complex vector space which we denote Vj. Going in the other direction, if one starts with a complex vector space W, then one can define a complex structure on the underlying real space by defining Jw equals Iw for all Ww. More formally, a linear complex structure on a real vector space is an algebra representation of the complex numbers C, thought of as an associative algebra over the real numbers. This algebra is realized concretely as which corresponds to I2 equals -1. Then a representation of C is a real vector space V, together with an action of C on V. Concretely, this is just an action of I, as this generates the algebra, and the operator representing I is exactly J. If Vj has complex dimension n, then V must have real dimension 2n. That is, a finite-dimensional space V admits a complex structure only if it is even-dimensional. It is not hard to see that every even-dimensional vector space admits a complex structure. One can define J on pairs E, F of basis vectors by J equals F and JF equals -E and then extend by linearity to all of V. If is a basis for the complex vector space Vj, then is a basis for the underlying real space V. A real linear transformation A. Vv is a complex linear transformation of the corresponding complex space Vj if and only if A commutes with J, i.e., if and only if likewise, a real subspace U of V is a complex subspace of Vj if and only if J preserves U, i.e., if and only if. Examples. Cn. The fundamental example of a linear complex structure is the structure on R2n coming from the complex structure on Cn. That is, the complex n-dimensional space Cn is also a real 2n-dimensional space, using the same vector addition and real scalar multiplication, while multiplication by the complex number I is not only a complex linear transform of the space, thought of as a complex vector space, but also a real linear transform of the space, thought of as a real vector space. Concretely, this is because scalar multiplication by I commutes with scalar multiplication by real numbers, and distributes across vector addition. As a complex n times n matrix, this is simply the scalar matrix with I on the diagonal. The corresponding real 2n times 2n matrix is denoted J. Given a basis for the complex space, this set, together with these vectors multiplied by I, namely form a basis for the real space. There are two natural ways to order this basis, corresponding abstractly to whether one writes the tensor products as or instead as. If one orders the basis as, then the matrix for J takes the block diagonal form. This ordering has the advantage that it respects direct sums of complex vector spaces. meaning here that the basis for is the same as that for. On the other hand, if one orders the basis as, then the matrix for J is block anti-diagonal. This ordering is more natural if one thinks of the real space as a direct sum of real spaces, as discussed below. The data of the real vector space and the J matrix is exactly the same as the data of the complex vector space, as the J matrix allows one to define complex multiplication at the level of Lie algebras and Lie groups. This corresponds to the inclusion of GL in GL and GL in GL, GL less than GL and GL less than GL. The inclusion corresponds to forgetting the complex structure, while the subgroup GL can be characterized as the matrices that commute with J. GL equals the corresponding statement about Lie algebras is that the subalgebra GL of complex matrices are those whose Lie bracket with J vanishes. Meaning, in other words, as the kernel of the map of bracketing with J. Note that the defining equations for these statements are the same, as AJ equals YAR is the same as, which is the same as, though the meaning of the Lie bracket vanishing is less immediate geometrically than the meaning of commuting. Direct sum. If V is any real vector space, there is a canonical complex structure on the direct sum V given by the block matrix form of J is where is the identity map on V. This corresponds to the complex structure on the tensor product compatibility with other structures. If B is a bilinear form on V, then we say that J preserves B if for all U, VV. An equivalent characterization is that J is skew-adjoint with respect to B. If G is an inner product on V, then J preserves G if and only if J is an orthogonal transformation. Likewise, J preserves a non-degenerate, skew-symmetric form omega if and only if J is a symplectic transformation equals omega. For symplectic forms omega, there is usually an added restriction for compatibility between J and omega, namely for all U and V. If this condition is satisfied, then J is said to tame omega. Given a symplectic form omega and a linear complex structure or J, one may define an associated symmetric bilinear form GJ on VJ. Because a symplectic form is non-degenerate, so is the associated bilinear form. Moreover, the associated form is preserved by J if and only if the symplectic form is. And if omega is tamed by J, then the associated form is positive definite. Thus, in this case, the associated form is a Hermitian form and Vj is an inner product space. Relation to complexifications. Given any real vector space V, we may define its complexification by extension of scalars. This is a complex vector space whose complex dimension is equal to the real dimension of V. It has a canonical complex conjugation defined by if J is a complex structure on V, we may extend J by linearity to Vc. Since C is algebraically closed, J is guaranteed to have eigenvalues which satisfy lambda 2 equals -1, namely lambda equals plus or minus I. Thus we may write where V plus and V minus are the eigenspaces of plus I and minus I, respectively. Complex conjugation interchanges V plus and V minus. The projection maps onto the V plus or minus eigenspaces are given by so that there is a natural complex linear isomorphism between Vj and V plus. So these vector spaces can be considered the same, while V minus may be regarded as the complex conjugate of Vj. Note that if Vj has complex dimension n, then both V plus and V minus have complex dimension n, while Vc has complex dimension 2n. Abstractly, if one starts with a complex vector space W and takes the complexification of the underlying real space, one obtains a space isomorphic to the direct sum of W and its conjugate. Extension to related vector spaces. Let V be a real vector space with a complex structure or J. The dual space V** has a natural complex structure or J** given by the dual of J. The complexification of the dual space C therefore has a natural decomposition into the plus or minus I eigenspaces of J**. Under the natural identification of C with asterisk, one can characterize plus as those complex linear functionals which vanish on V minus. Likewise, minus consists of those complex linear functionals which vanish on V plus. The tensor, symmetric, and exterior algebras over VC also admit decompositions. The exterior algebra is perhaps the most important application of this decomposition. In general, if a vector space U admits a decomposition U equals ST, then the exterior powers of U can be decomposed as follows. A complex structure J on V therefore induces a decomposition where all exterior powers are taken over the complex numbers. So if Vj has complex dimension n, then the dimensions add up correctly as a consequence of van der Waals identity. The space of forms lambda p q Vj asterisk is the space of multilinear forms on Vc which vanish on homogeneous elements unless p are from V plus and q are from V minus. It is also possible to regard lambda p q Vj asterisk as the space of real multilinear maps from Vj to C which are complex linear in P terms and conjugate linear in Q terms. See complex differential form and almost complex manifold for applications of these ideas.